Hi viewers. Welcome to this presentation on interconnected systems with synchronous link. Performance of grid system was encouraging because of benefits of improved stiffness due to increased system bias and inertia. Frequency changes are slow and small. Interconnection with neighboring system is beneficial to both the systems. It facilitates power assistance to each other during distress condition. It is also necessary to draw share of power from central sector pooled power plants such as NPC, NTPC and NHPC etc. Hence primarily regional grids were established with interconnections of neighboring state power systems. So operating criteria has also revision. Review of previous analogy of water supply system with modification. Water supply system setup is modified accordingly. There are two tanks with its inflow and outflow lines as in the figure. Both the tanks are connected at bottom by a pipeline with valve IC. Condition when interconnecting line valve IC is closed. In this condition both the systems are isolated and operate independently. Water level in tank A is exclusively regulated by control valve CGA and CLA and it is no influence on water level in tank B. Similarly, water level in tank B is exclusively regulated by control valve CGB and CLB and it is no influence on water level in tank A. Condition when interconnector valve IC is opened. Now both the systems are connected and there is passage for water flow in either direction. Now any variation of inflow or outflow in either system reflects in both the systems. Consider control valve CLA is opened to increase outflow. Water level in tank A drops because outflow is more than inflow. So inflow through CGA increase due to increased head HGA. So also outflow through CLA decreases due to decreased head HLA. Now dropped level in tank A will be lower than that in tank B. So some water flow through interconnecting line from high level in tank B to low level in tank A. Consequently, water level in tank B also drops. Hence, inflow through CGB increases due to increased head HGB and outflow through CLB decreases due to decreased head HGA. Increased inflow and decreased outflow in tank B results in excess water that flows to tank A. This process continues till total inflow equals total outflow. Consider other case when inflow through CGB is increased. So level increase in tank B and also in tank A. Therefore outflow through CLB as well CLA increase and inflow through CGA as well CGE decrease. This process continues till total inflow equals total outflow. Level variation is smaller than independent systems because automatic flow adjustment due to change in level occurs simultaneously in both the systems. Summary: 1. Level variation in one tank reflects in other tank and flow adjusted in both. 2. Water level in both the tanks remains same. 3. Water transfer between tanks via linked line as per situation. Power system also operates in similar manner. Consider to power systems A and B. Both the systems may operate independently as per load and generation within the system when isolated. Frequency may be different in both systems, and influence of mismatch occurred in one system has no effect in other system. But the systems operates in coordination when connected by AC tie line, synchronous interconnection. Consider increase of X megawatt load in system A, frequency drops due to shortage of generation against increased demand. Frequency will be same in both the systems because of interconnection. Generation increase in system A as well in system B by governor control due to drop of frequency. Similarly, power demand of load in system A as well in system B reduces with drop of frequency on account of frequency-dependent loads. Primarily, power shortage occurred in system A due to increase of load. This shortage is partially compensated by increase in generation and decrease of demand within system A. System B has no shortage of power, but there is increase in generation and decrease of demand with drop of frequency in system B also. Hence, there will be excess power in system B. This surplus power from system B flow to system A to compensate the shortage. In other case, when system frequency rise during loss of load in system A, generation in system A as well as in B will reduced by governor control with rise of frequency. Power demand of load in system A as well in system B increase with rise of frequency on account of frequency-dependent loads. Excess power in system A is partly adjusted within system by drop in generation and increase of load demand. Remaining excess power transfer to system B to fill the gap occurred due to drop of generation and rise in demand. Frequency variation is smaller compared to isolated system because of autocorrective action in both the system. Summary: 1. Mismatch occurred in one system is experienced and responded by other system. 2. Frequency remains same in synchronous interconnected systems. 3. Power transfer between the systems via tie line as per situation. Consider interconnected systems A and B operating with following parameters. System A demand 15,000 megawatts, generation 15,000 megawatts and bias 600 megawatts per hertz. System B demand 10,000 megawatts, generation 10,000 megawatts and bias 400 megawatts per hertz. Operating frequency 49.90 Hz. Now system A has 300 megawatts generation loss. Combined bias is equal to 600 plus 400 equals 1000 megawatt hertz. Frequency drop is equal to 300 by 1000 is equal to 00.30 Hz. System gain in A is equal to 00.30 times 600 is equal to 180 megawatts is partial compensation. System gain in B is equal to 00.30 times 400 is equal to 120 megawatts is surplus power. This 120 megawatts transfer from B to A. Shortage of 300 megawatts in system A is adjusted by 180 megawatts gain within system A plus 120 megawatts received from B. Combined systems stabilize at 49.90. 00.30 is equal to 49.60 Hz after loss of 300 generation in system A. Request: please subscribe and share with others. Viewers' comments welcome. Thank you, viewers. Bye until we meet again in next episode.